Good morning. Welcome to the lesson 10 of industrial instrumentation. In this lesson, we will study LVDT. The full form of LVDT is the linear variable differential transformer. It is basically an inductive based sensor or inductance based sensor, and primarily it is used for the measurement of displacement. However, I can use it for measurement of pressure and other process parameter also. In this particular lesson, we will consider the the basic concept of the LVDT, its circuitry, its signal conditioning circuits and its basic constructions, and how you design an LVDT. These are the basic things which we will discuss. Even though I have not written the contents of this lesson will be the LVDT, its construction, its signal conditioning circuit, lead network, lag network, phase sensitive demodulation circuit, as well as some design equations of LVDT. So, at the end of this lesson, the viewers will know the basic construction of LVDT, what are the signal conditioning circuits are to be used, what are the precautions you have to make it, its sensitivity, all those things will be studied in details in this particular lesson. It is a sensor for displacement measurement. You see, this is our basic LVDT. You can see here that you have a primary here. There are 3 windings. Look at very carefully. We have one primary and 2 secondaries, 2 similar exactly identical secondaries, right. Actually, should be also if I take should be also So, the excitation voltage will be here, it will come here and AC excitation voltage. So, it will be any voltage between 3 to 15 volts and 50 to 20 kilohertz and 2 different secondaries. Here we can see the basic construction. You see here on a bobbin the primary is owned and the 2 secondaries are owned in this fashion, right. Later on we will see that we will connect these 2 secondaries in oppositions, that will come later on. And you see there is a core, iron core, which will move up and down, right. This is the iron core which will move up and down. Interestingly, you see that if this core moves up, so there will more linkage between this and this. So, the mutual inductance between this coil and this coil will increase and the mutual inductance between this coil and this coil will decrease. So, at geometrical null position, mutual inductance between this and this primary and this secondary and this primary and this secondary will remain same, right. Now, let us go to the instrumentation lab of IIT Kharagpur and have a look on the LVDT. You see LVDT, linear variable differential transformer, it has one primary and 2 secondaries. The secondaries are usually connected in opposition to get a null position, and to after doing the phase sensitive demodulations, I can sense on which side of the null position the core lies. You see here the core is there, soft iron core, which will move like this, So, now I am moving, it will move like this. And then since there are 2 secondaries, what will happen if you put in opposition, obviously you will get some output voltage, and at null, when it is at the exactly at the null position, so 2 secondary coils will be output voltage will be nullified and I will get 0 voltage, but any position other than that will give you non-zero output voltage. So, LVDT already we have discussed in detail. So, this is actually pictorial view of the LVDT. Welcome back to classroom again. So, we have seen the construction of an LVDT and how it works. Actually, this core will if you look at this core will move up and down. this core will move up and down, and I will get the different mutual inductance, also the voltage also will be changed, and there will be phase difference between the input and output. So, that is actually we have written in a nice way. You see the flux formed by the primary is linked to the two secondary coils, inducing it will be an AC voltage in each. An iron core which moves through the bobbin without contact provides a path for magnetic flux linkage between the coils. The position of the iron core controls the mutual inductance between the primary and two secondary coils. This is most important thing, right. And usually we find the entire LVDT assembly we put, in some cases we will put under another casing, so that it will not be influenced by the other external magnetic field. Obviously, it depends on the magnetic fields. So, in some cases we will find that we will put the entire assembly, so that the external magnetic field will not affect the output voltage, because we want that our output voltage will be a function of the position of the core of the LVDT. Now, see, this is the we have given the if you look at the screen, you see we have given the excitation voltage, the sinusoidal voltage in the primary, and the two secondaries are identical. So, obviously, I will get two secondary voltages E 1 and E 2. We are assuming in these cases that the core is in null position, that is geometric null position. So, I am getting excitations of equal phase difference between input and output. This is our input or excitations. I am not telling it input, because input in the case of LVDT is the displacement which will give on the core, and output is the output voltage, and in this case is E 1 and E 2, right. Now, you see that there is a equal phase difference between input, since the two secondary coils are identical in nature. So, there will be equal phase difference in the two. So, you have seen that if you not consider, you might be there will be some attenuation, obviously there will be no question of amplification. So, there will be some attenuations we will get, but we have ignored that part. So, we have assumed that you will get the equal magnitude in the both secondaries. Now, secondaries, now you see LVDT we never use two secondaries separately, we always put the two secondaries in opposition. What is that thing? If you look at the board, our digital board, you see here that excitations we are giving here, these are core positions, we are 3 to 15 volts, 50 hertz to 20 kilohertz we are giving, and output voltage, you see the two secondaries here, these two secondaries are in opposite, there is no connection at this point, please note there is no connection at this point. So, this is one secondary and it is connected to the bottom, and it is coming like this one. What is the advantage of this one? You see in these cases, advantage is when this core is at the geometric null position, you will find that the output voltage E 0 will be 0. So, if I put this core slightly up and slightly down, I will get a non-zero output voltage, right. So, if I put this core slightly up, I will get a non-zero output voltage, because what will happen in this case, the two secondary output voltage are exactly in opposition, and this two will cancel out, I will not get any voltage at the output, right. Now, see, this is the output voltage we have drawn, okay, with respect to time, when for the different positions of the cores. Since these two secondaries are in opposition, you will find, if you look at the board or in the oppositions, you will find that core, this is the core at the null position, theoretically this should be exactly 0. So, see here, even though we are giving some excitation voltage which is sinusoidal voltage, I am not getting the output voltage, since the two secondary voltages will cancel each other. Whereas, you see when this core is above null, I will get a voltage like this one with a phase shift. If the core is below null, I will get a phase shift, a 180-degree phase shift, okay, separate opposite to the core above null, exactly, got it. This is necessary, because in some situation I must know in the which position of the core lies in which position, whether it is above null or below null. You see here what will happen, it is slightly we are getting like this one, right. So, you see these two phases are exactly out, that means it is 180 degree out of phase, right. There is a phase difference between this input voltage and this, or excitation voltage and this, and excitation voltage and this, but these two voltages, when the core is above null and when core is below null, the two phase difference is exactly 180 degree out of phase. Now, you see this is the our, now we have taken the magnitude of the output voltage, right. We have taken, that is the reason we have written here E naught mod, absolute value of the output voltage we have taken. Now, I change the position of the core and measure the output voltage, right. For suppose for x centimeter, 1 centimeter, what is the output voltage I have plotted. Then for x equal to 2 centimeter, what is the output voltage I have taken. For x equal to 3 centimeter, what are the output voltage I have taken, right. And these voltages I have plotted like this, clear. So, you see we are getting a linear curve, that means the relation between the displacement and the output voltage when the core is in when the secondary is in oppositions, exactly we are getting a relationship of linear relationship we are getting. So, at the geometric null position, so you see we are not getting an output voltage, right. Now, this is the what is plus x, what is minus x. Plus x, if I move the core in one side of the, suppose if I take the looks like this one, suppose I have a core here, right. This is my output voltage x naught. So, this is the position x equal to suppose 0. If I put it up, suppose this position. So, if I put it I am taking it positive displacement, if it put it down I get a negative displacements. So, in that respects I am calling it plus x and minus x. Now, if I put on the other side of the null position, I will also get the voltages, obviously with phase shift, but if I take a magnitude. So, I want the phase shift, I cannot identify that phase shifts, just if I take the absolute value. So, you see that I will get a curve like this one, and this you see it is falling down, because at that position what will happen, I am taking the core totally out of the bobbin. In that type of situations it will fall like this in both the cases. It is when it is going up, it is going out, and it is when it is going down like this one. You see I am getting a straight line relationship like this one. So, this is our the absolute value, the output voltage of the LVDT when in series opposition versus the position of the core, right. Now, applying KVL, if I take the equivalent circuits, if you look at applying KVL on the primary side, I can write, you see, IP Rp plus Lp dIp by dt minus Ex equal to 0 and Ip equal to Ex Rp plus Lp d. Second, if I go back, if I look at that will be better. If I go back here, yeah, this is actually should be, yes, I am sorry. You see, this is our equivalent circuit of LVDT. We have taken here, this inductance is Lp, primary inductance, this is primary resistance Rp, this excitation voltage Ex, and this is the resistance of the, there are two secondaries. We are taking the, if you assume the two are exactly identical. So, I can take this inductance is Ls by 2, this resistance is Rs by 2. So, we will get a simplified equation. This is the M1 is the mutual inductance between the primary and the one of the secondary. This M2 is the mutual inductance between primary and one of the secondary. This is the output voltage ES1 and this is the output voltage ES2, that means voltage source here, and this is RS2, and this for the time being we have not connected. So, we are connecting an RM, a meter impedance, okay, when there is a current is flowing through the this circuit, right. So, if I now draw the write the KVL around this loop, I want to write the KVL around this, that means in the primary side I will get if I go back, see if I now see ES1 and ES2 will try to induce voltage in the primary. However, this will nullify since it is in series opposition, right. What is ES1 and ES2? So, already we have seen. So, if the ES1 and ES2 will try to induce the voltage in the primary, and this will nullify since it will be is in series opposition. Now, if I go back, you see can see here. So, you see this is our basic equations. Okay. Oh, I am sorry. Now, see here if I apply a KVL around primary sides, I will get equation like this one. Already we have seen the equivalent circuits of an LVDT. So, if I apply the KVLs, I will get equation like this one, IPRP plus LP DIP by dt. Now, you see and so IP equal to Ex, where D is the operator. So, as before we know what is D, we know that D equal to D by dt, right, D by dt. So, that is the operator. Okay. So, I can come back, you see here, and Ex equal to Rp plus Lp d, and induced secondary voltage Es1 is M1 dIp by dt, and Es2 and Es1 already we have seen. What is this? If I go back, you see Es1 is this one and Es2 is this thing, right. So, this is the induced secondary voltage, right. So, this is our actual equation. So, you see the induced secondary voltage, this is applying on the primary sides, but in the secondary sides this will induce a voltage like this one, Es1 equal to Es2, Es1 equal to M1 into dIp by dt, and Es2 equal to M2 dIp by dt. Okay. So, all with respect to the primary current, right. Now, you see this is already we have discussed. Now, let us look at. So, Es1 and Es2 will try to induce voltages in the primary, however, this will nullify since it is in series opposition. So, find the, so that problem. So, the net secondary voltage if I look at Es or E naught whatever you say equal to Es1 minus Es2. This will be equal to the if you look at the expressions which you have seen. So, M1 minus M2 dIp by dt, because Es1 equal to M1 into dIp by dt and Es2 equal to M2 into dIp by dt. So, Es1 minus Es2 M1 into minus M2 dIp by dt. The net mutual inductance M1 minus M2 varies linearly with the core motion. For a particular core position, E naught equal to Es equal to M1 minus M2 d operator LP d plus RP Ex, right, excitation voltage. Now, you see this E naught by Ex, I can write excitation output voltage by, if I normalize the output, it will be M1 minus M2 by Rp d operator tau p d plus 1, where tau p equal to Lp by Rp, right. Now, you see here that this is the time constant. So, this is a first order system. So, it is a time constant of the system. Now, E naught by Ex if I look at, now obviously what will happen, where is the x, where is the position? Position is here in the inside the, if you look at the digital board is M1 and M2, because this is directly proportional to the position of the core, is not it? This M1 and M2 directly depends on the position of the core. So, you see this output voltage also depends on this value of the M1. So, all other things will remain constant, M1 will vary and M2 also will vary, while the if I move the core up, then what will happen? If they move the core up, what will happen? The M1 will increase, M2 will decrease. If I decrease the, if I make the core down, M2 will increase and M1 will decrease, is not it? So, there it is this x is hidden within this M1 and M2. So, obviously, this output voltage will be proportional to the position of the core or x, right. So, if I write in the frequency domain, so it will be like this one M1 minus M2 Rp square under the square root omega tau p square plus 1 with an angle phi. It is not come. So, the angle will look like this, right. So, this is the magnitude, this is the magnitude part and this is the your phase part. So, what is phase? Let us look at. So, you see the phase is equal to pi by 2 minus tan inverse omega tau p, right. So, the phase also depends on the frequency. Tau p is a constant. So, in fact, I can make omega tau p constant because tau p does not depends on the position of the core, is not it. Tau p depends on L p and R p. You see here this is a constant for a particular LVDT. Omega is the excitation frequency. If I keep constant, it will also remain constant. So, phi equal to pi by 2 minus tan inverse omega tau p, this will remain constant for a particular excitation frequency. If necessary, I can make it 0 also. If I can cancel, if I make tan inverse omega tau p equal to exactly equal to pi by 2. So, this will be cancelled, there will be no more, but sometimes this is not possible. So, you will use some lag network or lead network to kill the phase I mean lag or lead, right. So, I can make the phase compensation with simple RC circuit. Let us look at that. If the input impedance of the voltmeter, now you see the all the analysis so far whatever we have made, we are assuming that there is no current is flowing to the secondary. Current is not flowing to the secondary because we are assuming that we are measuring this impedance, we are connecting that secondary is open circuit, but most of the cases it is not true. Secondary we will connect some, but you can say to some, I mean if I to some I mean approximation this is also true, because we will connect a very high input impedance. Suppose if I connect a CRO cathode ray oscilloscope to measure the voltage output E naught. So, obviously, it is a very high input impedance. So, in that type of situation, so Rm will be very high. So, I can assume almost that the your secondary is open circuit, but if I assume, so the Is will be 0. But obviously, if I take the finite case, if we take assume that there is some current is flowing to the secondary. So, in that case we assume that the finite resistance Rm, meter resistance is Rm and a current Is is flowing to the secondary, because if you take a finite resistance Rm, so obviously the current also will flow. Previous analysis we have seen that there is no current is flowing to the secondary, only two voltages Es1 and Es2 was induced due to the mutual inductance between the primary and the two secondaries, right. So, in that type of situations my equation is, if I look at the digital board, it will look like Ip Rp plus Lp dIp minus M1 minus M2 dis equal to minus e to the power e x subscript x equal to 0. So, if I can write this equation M1 minus M2, this will be equal to dIp plus Rs plus Rm Is plus Ls dis equal to 0. So, if I mean take all this, so I can write the simplifications E naught by Ex d M1 minus M2 whole square Lp Ls d square plus Lp Rs plus Rm Ls Rp d plus Rs plus Rm Rp, right. This is equation number 3. So, lag network, as I told you, we need some lead and lag network. So, lag network looks like this one. You see this is a phase, this is a circuit if there is a lagging phase angle. If there is a phase angle is lagging, in that situation, so we will connect this is our lag network. So, it will kill the lag and it will have the output voltage will be in phase with the input voltage. It is not very important, most of the cases you will find, right. So, this is a lag network for compensation of the leading phase angle. If the phase angle is leading, we can use this lag network. Lead network, similarly, if it is lagging phase angle, I can use a lead network. So, lead network just interchange with capacitors and the inductor and capacitors and the resistance, I will get a lead network. So, it is a leading phase angle, it will look like this one. The frequency of excitation voltage applied to the primary winding can range from 50 hertz to 20 kilohertz. The power requirement is usually less than 1 watt and the sensitivities of different LVDTs vary from 0.02 to 0.2 volt per millimeter of displacement per volt of excitation applied to the primary coil, right. This is typical sensitivity, it is very sensitive devices. Now, you see most important thing of the LVDT is, you see it is a displacement sensor as I told you, but directly you can displacement, in other case you can use it for, you can use it for a load sensor, you can use it for a pressure, if you use it in conjunction with the diaphragm you will find it is used as a pressure sensor. You can use it as a flow meter. If you connect a you see that if you connect a to the bob of a rotameter, you will find that this will be used as a flow meter, as indication of the flow. So, all these different applications are there, but directly it is actually measuring the displacement. Now, other type of simplest form of displacement measurement is just a potentiometers. Okay. A simple potentiometer, if I look at, you see, if I connect like this one, suppose I have a like this one. So, let me take another page, that will be better, or I will take a different color. You see what will happen. So, I have connect, sorry. Let me take a new page. A simple resistance, a rheostat or a potentiometer pot, what we call. Suppose I have a wiper or jockey. In the case of potentiometer, we call it wiper. In the case of rheostat, we call it jockey. So, if the jockey moves in these directions, then what will happen? I will give some excitation voltage, suppose, and I am measuring the voltage on this one, E naught. Suppose this excitation, then what will happen? This output voltage will be a function of this displacement, is not it? Suppose this is x. So, this simple a potentiometer can also be used as a displacement sensor. However, the difference between the potentiometer and first of all the potentiometer and the LVDT, number one is its resolution. Resolution of LVDT is extremely good. Please note the resolution good means its numerical value will be less. And another thing is you will find that sensitivity in both the cases I can change. I can change the excitation voltage Ex, the excitation voltage of the, if I look at the digital class, if I change the excitation voltage, my output will also increase, or I can modify the I am not talking about this. I am talking about the resolution. Resolution in find, you see that whenever a potentiometer, if I look at the digital class, you will find that the potentiometer here what will happen, you see it will, even though I am showing here that it is getting contact only one turns, but you will see the actually potentiometer looks like this one, is not it. So, it will always, this wiper will contact more than 1 or 2 windings. So, resolution will basically depend how closely you make the windings, it is possible for you to make the windings, as well as whether this wiper or jockey is getting connected to one winding or 2 windings. But that is not the case in the case of and that is not the case for LVDT. So, LVDT what will happen, you see there is no contact between the wiper, which is basically a core, movable core, and either primary or secondary. So, the resolution I could say it is it's first of all life will also increase. You see here it in the case of, if you look at the digital class, you see that what will happen that in this case that this core will, this wiper will move, and after a few use you will find this wear and tear, it is called, this contact will become noisy, because the contact also depends on how much pressures you are giving. That type of cases does not arise in the case of LVDT, because LVDT I have core, this bobbin, and inside the bobbin this core is moving, is not it. So, there is no physical contact. So, life is almost infinity, you can say the mean time between failure is very high. Moreover, resolution is also high, because resolution here is very small. Small means good, extremely high, because in this case you see there is no question of even though whatever the windings we have on the outside, that does not depend, that does not matter how fine and how close those windings, is not it, because the resolution here depends on the magnetic linkage between the two. It does not depend on the physical position or the physical number of coils which is get in touch with the wiper. So, that is a great advantage of the LVDT. So, that is we have seen, we have written, you see there is no contact between the core and the coils, therefore, the friction is eliminated, thereby giving infinite resolution and no hysteresis. This is another important. You see in the case of potentiometer there will be a certain amount of hysteresis you will find, but there is no hysteresis in this case. No contact also ensures that life will be very long with no significant deteriorations of performance over this period. The small core mass and the freedom from the friction gives the sensor the some capability for dynamic measurements. Now, phase sensitive demodulation is very important in the case of LVDT, because LVDT we have seen that if the core moves up and down, I mean if I look at, you see we have seen that I have a primary and two secondaries, like this one, you see this moves, see moves up and down, what will happen? I will get output, no, is not it. See, if I move up, I will get some sinusoidal voltage, if I move down, I will also get the same sinusoidal voltage, but how will I know on which side of this one, whether it is lying whether it is lying up the mid position, null position, or below the null positions. So, for that reason I have to make the phase sensitive demodulation of the circuit, I mean the output. If I can make phase sensitive demodulation, that means in that cases we will separately full wave rectify the output to two secondary voltage, then make the algebraic sum of the two. So, one side I will get positive voltage, other side I will get a negative voltage, right. You see this is a phase sensitive demodulation circuit. You see the each half is actually rectified with a full wave rectifier. In all the cases, whether if this is positive, this is negative, you will find the current is flowing to this direction. If this side more positive and this side is more negative, current is also flowing to the same direction through the resistance R. Similar the case in the lower half, that means in the other secondary. So, these two voltages we are making algebraic sum. If I can make this algebraic sum, then what will happen? You will find that the output voltage, polarity of the output voltage will depend on the position of the core, that means whether the core is above null or below null, right. If it is above null, it will be positive, if we assume positive. If it is this core is below null, it will be negative, right. So, this is the phase sensitive demodulation circuit. Now, see the dynamic displacement measurements. If the LVDT is to be used to measure dynamic displacement, the carrier frequency should be 10 times greater than the highest frequency component in the dynamic signal. We will show the phase sensitive demodulation output after few slides. The excitation voltage ranges from 3 to 15 volts, right, because in some situations I may need to make the dynamic measurements, even though frequency should not be that high. So, for dynamic measurement, the frequency of the excitation voltage should be much greater than the frequency of the core movement. If a frequency ratio of 10:1 or more is feasible, a simple RC filter may be adequate. Now, this is you see the demodulator output for different positions of the core. If you look at, if the above null, I am getting a voltage like this one, this can be passed through an RC filter. So, it will be smoothen out, you will get complete DC. Core at null, obviously I am not supposed to get any voltage, so 0, and core above null, it is like this one. So, you can see the polarity of the voltage is getting changed, right. Now, interestingly, you see that what will happen in this case, you will find if I take the blue one, that means in this case, if I plot the output voltage with polarity, this is plus E, obviously this since it is fully rectified. So, it is DC, even though our excitation voltage is AC, now our output is DC, because the two secondaries we are fully rectified and we are adding it algebraically. So, the output voltage will look like this one. I am sorry, let me take another page. So, right. So, this is our output voltage, this is positive, this is minus E naught, this is x plus x 0, this is minus x. As I told you, plus x minus x nothing but the above null, or the one side of the null is positive. If one side of the core movement is positive, or one side of the null of the core movement is positive, other side of the movement on the other side of the null is we are taking negative. So, you see we are distinctly we are getting is a linear relationship, but along with the change in the magnitude. This is very now I can tell whether it is above null or below null looking at the voltages. This is very important. Look at the digital class. If I look at, you will find that the if it goes below null, so obviously what will happen? So, I will get a negative voltage. Now, this you see the again we are coming back to our RC circuits, which is used for our simple RC circuits to make our for dynamic measurements. In that case, the carrier frequency should be much higher. That means, excitation frequency should be at least 10 times higher than the maximum expecting dynamic signal in the LVDT, right. That means, what is dynamic signal here? Dynamic signal is the movement of the core is the input, right. Input is the movement of the, so that input component frequency of the dynamic input component should be 10 times lower than the frequency of the excitations of the LVDT. Clear? So, if I have that type of, I can have a simple RC filters. So, this is a first order RC filter. So, that will suffice, that I can extract the original signal. So, the response will look like you see E 1 by E naught, this output voltage, C E 1 by E naught. So, it is minus 20 dB per decade. So, it is the corner frequency omega equal to 1 by tau, right. So, low pass filters and its frequency response. Now, another thing, even though I said that in the case of LVDT you see that the two secondaries are exactly identical, but you know it is very difficult, absolutely difficult to make two secondaries exactly identical, and the harmonics also will be present in the secondaries, right. So, this will create problem, that means, this will make our circuit, this will make our circuit in such a way that I will not get 0 voltage at geometric null position, right. That is the thing we are seeing. The harmonics in the excitation voltage, if I look at the and stray capacitance between the primary and secondary will lead to non-zero voltage at geometric null position of the core. The mismatch of the two secondaries also plays a role in generating this null voltage as shown in the figure 12. Sorry, you see this is a null voltage. It is supposed to be 0, but there is no. So, the figure 2 is a null voltage. So, this you see here the null voltage, it is the voltage non-zero voltage I am getting at the geometric null position, right, because making two identical secondaries is almost impossible, right. So, what will happen, that will be some non-zero voltage will remain. Actually, what will happen if I look at the vector diagram, it looks like this. So, the two secondaries should be like this one. Okay. You see this is if the secondary current I s 1, this I s 2. If these two cancels, it will look like that. But actually, what will have due to mismatch, you will find one will be like this one, other one will be this one I s 1, I s 2. So, the resultant will go like this one. In this case, the resultant will go like this, right. If I take a different color, so the resultant will go like this, whereas in this case the resultant will go like this. So, clearly I am getting non-zero voltages, right. Now, this null voltage is a nuisance, we must kill it. So, there are various circuits available to kill this null voltage. One of the voltage you see null voltage reduction circuit, when the center tap primary excitation voltage source is available. If you have the center tap primary excitation voltage source, I can use this type of circuits, where you have seen that this center tap is grounded. Sorry, this is not ground, actually this is a core motion. So, it will come like this one, it will come out like this one, right. And you see here. So, I have a center tap primary source is available. So, this center tap is grounded with the ground of the one of the output terminals, and now I am getting outputs. In this case you will find the output voltage will be the null voltage will be 0, right. Now, figure 13 in next figure will show that if the center tap excitation voltage is not available, how it can kill this null voltage. It will look like this one. You see the figure 14, the null voltage reduction circuit when the center tap primary voltage source is not available. You see here this will vary this position, you see center tap is not available, 2 potentiometers it is dropped, this is grounded, this again is at previous case it is grounded. So, this will vary, okay, will vary the position of the, this is potentiometer, it is all the I mean voltages come across the potentiometer, will change the position of the core, position of the wiper, so that the output voltage will become 0. So, figure 14 shows actually method for null voltage reduction when center tap excitation voltage is not available. Here the potentiometer is adjusted until the minimum null voltage reading is out. If it can't 0, we can make, if we can't make it 0, make it minimum. So, that that will be, that means at a 0 null position, that some minimum voltages we will get, that will suffice in most of the cases. Now, how to design this LVDT? So, this thing you must see, this is our schematic of our LVDT, even though you see that these are the two primary windings, this is the primary windings, okay, because you see this is basically a cylinder sort of thing, right. It is cylinder, I mean here we have the this core, you see this iron core. So, this is our primary, okay, it is a coil like this one is the primary and two identical secondaries. Now, you see this length of the secondary we have given S, this length of the primary we have given P, two identical secondary of equal length, and Ri and R0 is the Ri is the inner radii and inner Ri and R0 are the inner and outer radii of the LVDT or assembly I should say, and La is the length of the armature or length of the core, right. This is our movable core, please note. Now, net induced EMF of the secondary coil is will be given by this, you see here. So, this is our net induced EMF in the output E j omega I p 4 pi n p n s mu naught p x upon 3 s natural log r o by r I 1 minus x square by 2 p square, equation number 4, where omega is the frequency of excitation voltage in radians per second, okay, and I p is the primary current, n p n s are the number of turns of primary and secondary windings, and R naught and R I is the outer and inner radii of the LVDT assembly I should say, and displacement of the core from the x is the displacement of the core from null position, from right from the beginnings we have used that one, and mu naught is the permeability of free space 4 pi 10 to the minus 7. Now, if you look at the nonlinearity term, this is our nonlinearity term, you look at this is our nonlinearity term, is not it, x square minus upon 2 p square, this is the nonlinearity term in the LVDT, right. So, the nonlinearity term x square minus by 2 p square in equation 4 is dependent on the length of the primary winding p for a desired range of x max, and the error due to nonlinearity I mean epsilon, the length of the primary winding is given by this p equal to x max upon root 2 into epsilon. So, this is actually the length of the primary. So, we will get from these expressions, question number 5. The length of the secondary winding is also given by this section, s equal to p plus x max. The length of the core and the length of the secondary are kept little more to accommodate the small spacing between the primary and its secondary windings, right. This is necessary, and you see if you look at, so this ratio, in fact this will be ratio, the ratio of R I by L A is about 0.05 and the ratio of R O by R I varies between 2 and 8. The number of secondary turns should be as large as possible to produce larger sensitivity, and since it is likely to be connected to high input impedance amplifier quite obviously and the meter, the secondary windings can be of finer wire, right. Now, you see that in the practical cases we will find it is very difficult to actually commercially, if you are not available, I mean LVDT, you can make your own LVDT, even though we have made in our laboratory also according to your need, but it is an excellent, and it is a it is an application, even though I say that the its applications in the measurement of process parameter measurement, that means it is usually used for the measurement of displacement along with the displacement with the it is used for the measurements of the pressure if I use a diaphragm gauge, okay, and it can be used for the measurement of measurement of flow. So, in the case of diaphragm you see how it is used. If I look at, you see here, you see you will find what they do if I look at the digital class. So, I have a stretched diaphragm, right. So, if I increase the pressure on this side, you see this diaphragm will be stretched like this. We will study this diaphragm very. Now, you see this interesting thing is that the linearity of the diaphragm depends on the how much is the displacement. Less is the displacement, we will have the better linearity, that means pressure versus. So, if I now connect a core of LVDT like this one, primary to secondary, right, output voltage, I have a getting excitation E x. Now, you see what will happen as the pressure increases, I will get that this core will move from the null position, I will get a non-zero output voltage E naught. I will not need any phase change demodulations of that type of thing, this is not necessary, because in the cases, in these cases diaphragm will move only in one direction, it will never move in this direction, clear. So, this will give you the output voltage, non-zero output voltage, right. Now, this is the one applications of LVDT. Other applications of LVDT, if I look at, you say that we have seen that the rotameter in many places. So, we have a channel like this one. So, the float is here. So, the flow is in this direction, it is coming out in this direction. So, what they do with a grommet sealing, they connect a core here, similar, two secondaries in opposition. Okay. See if I draw it nicely, it looks like this, you see. So, I have a bob here and it is flowing like this one, this sealing is there. So, output voltage. Now, E naught, sorry, E x. So, what will happen if the bob moves, this float moves, I will get a non-zero output voltage. So, the voltage will increase on the output side. It is quite obvious in the case of rotameter also, as the flow increases, this float will go up and up. This is another example of an LVDT. I can put some more examples. One of the examples of the another, pressure sensors, we will find that that our Bourdeau gauges basically depends on this type of pressure measurements. Okay. A C tube, okay, let me draw it nicely. We have a C tube like this one. Okay. So, this tip movement, I can connect if I connect an core of the LVDT here, again this will come here and this will go here, E naught, this excitation. What will happen, you see, if the core moves, then what will happen? If the pressure increases, as you know, this tip will try to move out. If it move out, so within the what will happen? So, this position of the core will change from the null position. So, I will get output voltage. So, even though measuring pressures, I am getting electrical output, even though I told previously in the case of Bourdeau gauge, it is very difficult to get the electrical output, but here you can see I can get the electrical output here by using an LVDT. So, this is several applications of the LVDT, even though it is basically used for the measurement of displacement. Moreover, it has a biomedical applications, even when the child is it is it is in mother womb. So, its respiratory signals also can be collected by using an LVDT, right. So, these are the different applications of an LVDT. Now, LVDT, as I told you, basic advantage of this type of devices is its sensitivity is also there. I can increase the sensitivity by increasing the excitation voltages, and I can increase the resolution obviously, which is much higher than the conventional or other displacement sensor. So, whenever I need a better resolutions, I need a better sensitivity, we have to use LVDT instead of simple potentiometers or linear potentiometers, which is used for measurement of displacements. With this, I come to the end of this lecture of LVDT.